speaker from Iran, Dr. Kamran Divaani-Aazar. He's a professor in Alzahra University, Tehran in Iran. He's also a researcher or affiliated with the IPM, Tehran. And his area of research is commutative algebra and algebraic geometry. And particularly, he is working in local cohomology and tight Collier theory as well. Welcome to Professor Kamran. So his form is to you to start. And he is talking about, today he's talking about relative homological rings and modules. Thank you. So please, Dr. Kamran.
Thank you for your invitation. And thanks the participants for being here. As you see, the title is Relative Homological Rings and Modules. First of all, I am going to explain the story behind the origin of homological rings and modules goes back to a celebrated characterization of regular local rings in 1954 by Auslander, Buchsbaum, and Serre. For giving this characterization, we need some notation. So we fixed some notation. For an ideal A, we denote the minimum number of generators needed to generate A by mu of A. We know that by crude generalized principal ideal theorem, the crude dimension of a local ring R should be smaller than or equal mu of M. If here equality holds, then we say that R is regular. So a local ring is regular if dimension of R is mu of M. There is a nice question regarding local rings. Is the localization of regular local ring at a prime ideal of R again a regular local ring? So for answering this question, we need a good characterization for regular local rings. This has been done by Auslander, Serre, and Buchsbaum. So here we have this promised characterization. Let R be a local ring with residual field K, then the following are equivalent. R is regular, projective dimension of M is finite for every R module M, and projective dimension of K is finite. These three conditions are equivalent for any local ring. Here people who want to enter the session, I should admit them. Maybe you do it by yourself, Alireza?
So I'm doing it, Dr. Kamran.
Yeah.
Yes.
So, but
We
since
are
you are
handling
co-host, you
those
receive the
things.
same message. No problem.
So I skip them. So I skip them.
Yeah,
Please, you do it yourself. Here we have this characterization. So here in second and third part, we have effect of homology. So this characterization should be considered as a homological characterization for regular local rings. You know, regular local rings originally are a geometric concept because for any variety, the coordinate ring of for any smooth variety, coordinate ring of any point on the variety is regular local. So regularness has a geometric nature, but by this characterization, it also has a homological nature. So this is the starting point for homological modules and rings. And using this, we can easily answer this question. It's just an exercise to solve this question by using this theorem. And then we have this characterization. we can extend the definition of regular local rings to arbitrary rings, not necessarily local. So we can define a ring R be regular if its localizations at any prime ideal be regular local. So we extend the definition of regular rings to general Noetherian ring. So then people studied more homological rings. After regular rings, there are other type of homological rings like complete intersection rings, Gorenstein rings, Cohen-Macaulay rings, surjective Buchsbaum rings, and quasi-Buchsbaum rings, and generalized Cohen-Macaulay rings. So here, Cohen-Macaulay rings are very important because there have been many conjectures regarding them. You know, there are some type of conjectures from 60s about they called homological conjectures, and most of them are concerned about these type of rings. And one of them is conjecture by Hockster about the existence of big Cohen-Macaulay algebras. So Cohen-Macaulay is very important. These type of rings also are important for after rings, I mean the other types, for varieties that are not smooth. So when we don't have a smooth variety, we deal with other type of rings. So some geometers call, after regulars, call these rings singularities. But we are not interested in this point of view. We're just interested in that all of these type of rings have homological characterizations. From Gorenstein onward, these type of rings have modulo-theoretic counterparts. So we have Gorenstein modules, Cohen-Macaulay modules, surjective Buchsbaum modules, and etc. And since Cohen-Macaulay rings are very important, many mathematicians try to extend this theory to a more generalized setting. One of the generalization of Cohen-Macaulay rings are relative Cohen-Macaulay rings. So, and this theory, the theory of relative Cohen-Macaulay modules, established by Hillas and Schenzel in 2008, and Rahrozager and Zakeri in 2015. I name these four people because for Hillas and Schenzel, they use the terminology of homological complete intersection. They don't use the notion of notation of relative Cohen-Macaulayness. The notion of relative Cohen-Macaulayness established by Rahrozager and Zakeri. But this is two names for one concept. So here we have, we mentioned to all four people for as inventor of this theory. So we are going to define relative Cohen-Macaulayness and then report some of their main properties. But for that, first of all, we need to recalling the definition of local cohomology. Let I be a non-negative integer for an R module M. Its ith local cohomology with respect to an ideal A is defined as follow. It's a direct limit of some X modules and is denoted by this notation. We denote the largest integer I such that this module is non-zero by this notation, and we call it cohomological dimension of M with respect to A. Also, we denote the smallest integer I such that this local cohomology is non-zero by this notation and call it grade of M with respect to A. Now we are in a position to define relative Cohen-Macaulayness. Let A be a proper ideal of R and M a finitely generated R module. Then M is said to be a relative Cohen-Macaulay if either M is AM or M is not AM and grade of A and M is cohomological dimension of A and M. So in other words, finitely generated R module M is a relative Cohen-Macaulay if there is at most one non-zero local cohomology. Because if we have this assumption here, all local cohomologies are zero. And this one means that we have just one non-zero local cohomology. So if we consider these two together, a module is a relative Cohen-Macaulay if and only if it has at most one non-zero local cohomology with respect to A. Here is a result in the original paper by Hillas and Schenzel in 2008. Let R be a local Gorenstein ring and A be a proper ideal of R. Denote the cohomological dimension of A by C and let D be the dimension of R over A. Suppose for any prime ideal here, the image of A at localization of R at P for any P here is complete intersection. Then the following three conditions are equivalent. The first one, R is a relative Cohen-Macaulay. The second one, this local cohomology is either injective envelope of residual field of R or zero. And all bus numbers of the only possible non-vanishing local cohomology satisfies this relation. They are either 0 or 1 depending on, this is the Kronecker delta. And
sorry, what is E of in the last slide? E R
sorry,
of K? What
delta,
is E?
E. It means E. This one you mean?
Yes, yes, yes.
E is the injective envelope of K.
Okay, okay, sorry. Okay.
So the other result is due to Rahruzaga and Zakiri. Let A be proper ideal of a local ring, and M be a non-zero A-relative Cohen-Macaulay R module. Denote its the cohomological dimension of M with respect to A by C. Then we have these two assertions. The first one says that injective dimension of M is finite if and only if the injective dimension of these local cohomology is finite. This is the only possible non-zero local cohomology. So this is finite if and only if this is finite. And then in second assertion, we have this nice formula between the injective dimension of this local cohomology and injective dimension of M. Now we are going to define a relative system of parameters. This is a very powerful tool for relative homological modules and rings. You know, in the ordinary theory of homological modules, most of them defined by a system of parameters. So if we have a good theory of relative system of parameters, then we be able to define relative counterparts of that those homological modules. So this is the definition. Let M be a finitely generated R module and A an ideal of R such that M is not equal to AM. As usual, C is the conjugate dimension of M with respect to A. A sequence of elements in A like X1, X2 of Xc is called a relative system of parameters for M if we have this relation. The radical of this ideal, the radical of these two ideals should be equal. So if we take R a local ring and take A be the maximal ideal of that local ring, then by this definition we recover the definition, definition of ordinary system of parameters. So the bad thing about this definition is that the ordinary system of parameters always exist, but a relative system of parameters maybe not exist. So we need to a characterization for knowing when they are exist. Here is we are prepared to give that characterization. Let B be an ideal of a ring T by mathematical rank of B, which is denoted by this symbol. We mean the least integer, non-negative integer n, such that there exist element y1 up to yn in T, such that the radical of B be equal to the radical of the ideal generated by these elements. Just as an easy exercise in local cohomology, one can see that for any R module M, we have this inequality. So now we can present characterization for existence of system of parameters, relative system of parameters. Let M be a finitely generated R module, A as before an ideal, and M is not equal to AM. Then A contains a relative system parameter of M if and only if we have this equality. That means we have this inequality if always we have this. If equality holds, then a relative system of parameters exists. So in a local case, when you take A be the maximal ideal of a local ring, one can see always we have this, always we have equality here, so always ordinary system of parameters exist. So we have this characterization, and it's quite easy to see it. Just by definition, one can check it. Now we give a characterization for system of parameters. Let A be an ideal of R, M a finitely generated R module with M different from AM, and C is this. And we have the needed assumption for existence of system of parameters, relative system of parameters. And let X1 up to Xc be some elements in A. Consider these two conditions. The first one, X1 up to Xc is an A relative system of parameter of M. And the second, cohomological dimension of A and M over X1 up to Xi multiplied by M is C minus I for any I from 1 up to C. Then always I implies 2I. If furthermore, A is contained in the Jacobson radical of R, then 2 also implies I. So if A is contained in Jacobson radical of R, these two conditions are equivalent. And now we can use a system of parameters for providing a characterization for relative Cohen-Macaulay modules. Sorry, I cannot see the chat box. If there is any question in chat box, please let me know.
Yeah,
So-
sure. We will
Thank
take
you.
care of those things.
So here is the characterization for relative Cohen-Macaulayness by using relative system of parameters. So let M be a finitely generated module with this condition, and this equality is needed for existence of relative system of parameters. Now consider these three conditions. The first one, M is a relative Cohen-Macaulay. Second, every a relative system of parameter of M is an M regular sequence. And the third, there exists an A relative system of parameter of M, which is an M regular sequence. Then always the first and the third one are equivalent. Furthermore, if A is contained in the Jacobson radical of R, then all of these three conditions are equivalent. So this is similar to the one of the characterizations of Cohen-Macaulay rings. We know that finitely generated module over a local ring is Cohen-Macaulay if and only if every system of parameters of M is M regular sequence. So this is the analog of that famous characterization. Here, maybe one thing that this is one may think that we can omit this. One may think that if A is A relative Cohen-Macaulay, then we have this automatically. But unfortunately, there is an example that it shows that this is not the case. The example is as following. Let K be a field and take S to be this power series ring. Let F, G, and H be these elements of S, and take R to be this quotient ring, and let A be the image of the ideal generated by F, G, and H in R. Then one can see easily that R is a complete intersection ring of dimension 3. Homological dimension of A is 1. And arithmetical of A is greater or equal to 2. So since these two are not equal by our characterization for existence of A relative system of parameters, there doesn't have any A relative system of parameters. On the other hand, since homological dimension of R is 1, and the zeroth local cohomology of R with respect to A is 0, we only have one non-zero local cohomology. So by definition, R is A relative Cohen-Macaulay, but because these two are not equal, we don't have any A relative system of parameter. Now we can define other type of relative homological modules. Before doing that, I should say something. Here, for type of rings below Cohen-Macaulay rings, surjective Buchsbaum rings, quasi-Buchsbaum rings, and generalized Cohen-Macaulay rings. We in a joint work with Akram Qambardoost, Tusi, and Zakiri, we established a relative counterpart of these type of homological rings. But for these type of homological rings that are above Cohen-Macaulay rings, in another research work with Ahad Rahimi and Paysapur Qobadian, we established the relative counterparts of these three type of homological rings and modules. In this talk, I mostly focused on this type of relative homological modules. So I am going to define relative Gorenstein-ness, relative Cohen-Macaulay, relative regularness, and relative complete intersectionness. Let A be a proper ideal of R and C be the cohomological dimension of A. Take M be a finitely generated R module. We call M a relative regular if either M is AM or M is different from AM, and A can be generated by an M regular sequence of length C, which is also R regular sequence. So M is called a relative regular in two cases. Either M is AM or M is different from AM, and we have C elements X1, X2 up XC, which generate A, and X1 up to XC is both M's regular sequence and R regular sequence. So this is the definition of a relative regular modules. And for Gorenstein-ness, we say M is a relative Gorenstein if these X modules are 0 for all I different from C. C is the cohomological dimension of A. So please compare these definitions with the original definitions of Gorenstein modules or regular modules. Of course, we don't have, we don't have in ordinary theory of homological rings and modules, we don't have any notion of regular homological, any notion of regular modules. And the third, M is called a relative maximal Cohen-Macaulay if grade of M with respect to A is C. So we have these three definitions, and here we have the definition of complete intersection rings. Let A be as before. Denote by math call R the A-adic completion of R. We say R is a relative complete intersection if there exists a ring T, a proper ideal B of T, and elements X1 up to XL in B such that these two conditions satisfied. The first one, X1 up to XL, is both a part of a B relative system of parameter of T and a T regular sequence. And T is B relative regular, and this quotient ring is isomorphic to math call R, and the extension of the ideals B and A in math call R are equal. So here you may ask why for these three types of relative homological modules, I define modules, I define them for modules, but here for rings. Here also we can define complete intersection, relative complete intersection modules, but the definition at that case would be more complicated, and I prefer to just bring here the definition of complete intersection rings. So it's natural to ask about the relation of these type of relative homological modules with the ordinary homological modules. So this is answered in this remark. Let R be a local ring with the unique maximal ideal M, and M a finitely generated R module. R is regular in the ordinary manner if and only if R is M relative regular. R is complete intersection if and only if R is M relative complete intersection. R is Gorenstein if and only if M is a relative Gorenstein, and M is maximal Cohen-Macaulay if and only if M is M relative maximal Cohen-Macaulay. And finally, M is Cohen-Macaulay if and only if M is M relative Cohen-Macaulay. So, I showed you an implication display for different type of homological rings. So we may ask whether the similar implication display holds for relative homological modules and rings? The answer is yes. We have in this regard this theorem. Suppose that the ideal A is contained in the Jacobson radical, then if R is a relative regular, then it is also a relative complete intersection. Also, we have this, if A is contained in the Jacobson radical of R, if R is a relative complete intersection, then it is also a relative Gorenstein. And we have this one, if every a relative Gorenstein module such that M is not AM is a relative maximal Cohen-Macaulay. And the fourth, every a relative maximal Cohen-Macaulay module is a relative Cohen-Macaulay. I end this section by three examples.
I have
Sorry.
one question. Could you please recall what is the difference between maximal cohomology, Cohen-Macaulay, and the a relative maximal Cohen-Macaulay and a relative Cohen-Macaulay? What is the
Sure.
Yeah, I missed.
Sure. Let me just 1 minute. Let A be a proper ideal of a ring and M finitely generated R module. So we say that M is a relative, and suppose that M is different of AM. We say that M is a relative regular if a grade of A and M is homological dimension of A and M. And we say M is a relative, maximal, Cohen-Macaulay, maximal Cohen-Macaulay if grade of A and M is cohomological dimension of A and R. Here we have M here, but here we have R. Since we have these inequalities, always grade of A and M is smaller than or equal cohomological dimension of A and M, and this is always smaller than or smaller or equal to this. So if these two be equal, then these two also has to be equal. So being a maximal Cohen-Macaulayness, relative maximal Cohen-Macaulay implies that M is a relative Cohen-Macaulay.
Okay.
This equality implies this equality. So,
okay. Thank you.
You're welcome. So how we covered the how to return the so you can see the slides.
Yes, we can see.
Yes. So in the first example, I provide an example of a relative Cohen-Macaulay module which is not relative Gorenstein. Let G be this cyclic graph with 4 vertices. Let K be a field and G be the above cyclic graph. Then the edge ideal of G is in this polynomial ring is this x1, x2, x2, y1, y1, y2, and y2, x1. Let A be the ideal generated by y1 and y2, and let M be S over IG. it is routine to see that Ig is equal to the intersection of these two prime ideals. So this is a minimal prime decomposition of Ig. And because of that, the set of associated prime of M consists of these two prime ideals. Since A is not contained in any of these two prime ideals, we have this grade of M with respect to A is at least 1. On the other hand, homological dimension of A and M is the maximum of these two. One can easily show this. It's elementary in local cohomology theory. So since these two are 1, their maximum also is 1. So here, always this is smaller than or equal to this. Since this is 1 and this is bigger or equal to 1, we have equality of these two. Grade of A and M and homological dimension A of A and M are equal. And so by definition, M is a relative regular. But M is not a relative maximal Cohen-Macaulay because grade of A in this ring is 2. Homological dimension of A in S is 2. For M being maximal Cohen-Macaulay, this grade should be equal to this. But we saw that the grade of M with respect to A is 1, and this is 2. So M is not a relative maximal Cohen-Macaulay. But in the previous slide, we saw that any A relative Gorenstein with M is different of AM has to be maximal relative Cohen-Macaulay. So since M is not a relative maximal Cohen-Macaulay, we conclude that M also is not a relative Gorenstein. So here we present an example of a relative Cohen-Macaulay module, which is not a relative Gorenstein. In this example, show that there are a lot of relative Gorenstein modules or rings. Take S to be this polynomial ring, where a field K, let M be its maximal homogeneous ideal, and take A, these be these monomial ideal, x1 to p1 up to xn to pn, and m1 up to m sub r are monomials in S. By a result in this reference, we have this x always are 0 for all I different from n. So, and also it's easy that the radical of A and M are equal. We have this equality. So from local cohomology, we know that two ideals with the same radical have the same local cohomology modules. So we have this equality between local cohomology modules. So cohomological dimension of S with respect to R is the same as the cohomological dimension of S with respect to M. But cohomological dimension of S with respect to M has to be its dimension, it's N. So we have this. Consequently, these X modules are all 0 for all I different from cohomological dimension of S with respect to A. So by definition, S is a relative Gorenstein. So here, a lot of a relative Gorenstein rings. And this example present plenty of relative regular rings. Take S as before, and let A be this monomial ideal. Then it's quite easy to see that S is a relative regular because A generate with here the cohomological dimension of S with respect to A is exactly L. So, and these elements are an S regular sequence. So A generate with exactly the number of L, which is the homological dimension of A in S, and these elements are an S regular sequence. So by definition, S is a relative regular. So in the next section, we will be focusing on Gorenstein modules. You know that it's a little somehow, let me RBLO.
We can't hear you, Professor Kamran.
Internet is not stable.
Yeah, I think so. No. Hello.
Can you hear me?
Yes, now we can hear you. Please share the slides
Net
again.
connection, sorry.
Yeah, it's okay.
So it's called
I think he's disconnected again.
Yes.
You are
Hear me?
muted. Yes,
Do you hear
now we
me?
can. Yes,
Sorry,
we
sorry.
can hear you.
Maybe changing between board and slides provide some problem. I will not do it again.
Okay. Okay, please share your slides again.
So here we have this. Let our
So,
let
Dr. Kamran,
Wait,
you need to share
sorry.
your slides again.
oh yeah.
Thank you.
So Control L. Do you see it?
yes.
So let
Okay, sorry.
let R be a D-dimensional Gorenstein ring. Sorry, let R be a D-dimensional local ring. It is known that R is Gorenstein if and only if it is Cohen-Macaulay and its top local cohomology is the injective envelope of its residual field. And if and only if these X modules are 0 for all I bigger than D. So here we have two characterizations for Gorenstein-ness. So we are interested to see whether there is an analog of this for relative Gorenstein-ness. The answer is yes, but for presenting this analog characterization for relative Gorenstein-ness, we need a definition. Here is our definition. Let A be a proper ideal of R and M be an R module. Then A relative injective dimension of M is defined as the supremum of I's such that X of R over A against M is non-zero. So what is the relation of this relative notion of injective dimension with ordinary injective dimension? We have this. If R is local and M is a finitely generated R module over R, then its ordinary injective dimension is its M relative injective dimension. So we have this characterization for Gorenstein modules, relative Gorenstein modules. Let M be a finitely generated module satisfying this condition and denote the homological dimension of A with C, then these three conditions are equivalent. M is A relative Gorenstein. The second, M is A relative maximal Cohen-Macaulay, and A relative injective dimension of the only non-vanishing local cohomology is 0. And the third, M is A relative maximal Cohen-Macaulay, and these X modules are 0 for all I bigger than C. We can record this corollary for ordinary Gorenstein modules. Let R be a local ring and M a non-zero finitely generated R module. These two are equivalent. So we can use the relative theory for establishing a corollary for ordinary theory of Gorenstein-ness. M is Gorenstein if and only if M is maximal Cohen-Macaulay in the topolocal cohomology of M with respect to maximal ideal is an Artinian injective R module. There are two classical theorems in commutative algebra. One of them is due to Boss. It's a characterization for Cohen-Macaulay local rings. It says that a local ring is Cohen-Macaulay, a local ring R is Cohen-Macaulay if and only if R admits a non-zero finitely generated R module with finite injective dimension. And there is a characterization for Gorenstein local rings. A local ring R is Gorenstein if and only if R admits a non-zero cyclic module with a finite injective dimension. So keeping these two classical theorems in mind, one may ask about having the analog of these two theorems in relative theory. Unfortunately, this is not the case. We have an example here shows that this is not the case. Take SB this ring and MB its maximal homogeneous ideal. A is the H ideal of C4 as before. We saw in example 2.13 that this is the minimal parameter composition of A. From these, we can have this short exact sequence. From this short exact sequence, we can deduce that dimension of S over A is 2. This local cohomology is 0. And the first local cohomology of S over A with respect to M is not 0. So depth of S over A is 1. By a result of Liouvsky, we know that for monomial ideals, we have this equality. Homological dimension is equal to projective dimension of this quotient ring. So this is due to a result by Lipsnick. And the second equality is just using deduced by using the Auslander Buchsbaum formula for projective dimension. So homological dimension of A is 3. Now, as S is Cohen-Macaulay in ordinary manner, I mean, we get that grade of A is the dimension of S minus dimension of S over A. So it's 4 minus 2. It's equal to 2. Thus, S is not a relative Cohen-Macaulay because we here its homological dimension is 3, but the grade is 2. Since these two are not equal, S is not a relative Cohen-Macaulay. But S over A is cyclic. So we have a cyclic from the definition of relative injective dimension. Oops. Here, it's from the definition, it's clear that this A relative injective dimension is less than or equal to projective dimension of R over A. So here, since this ring is regular, the projective dimension of any S module is finite. So A injective dimension of S over, sorry, this should be S over A is the, no, S is okay, sorry. This is less than this. So this is finite. Here we have S over R. It's a cyclic S module, cyclic non-zero S module with finite A relative injective dimension, but S, the ring, is not a relative Gorenstein, even it's not a relative Cohen-Macaulay. So this is a bad example for our theory. Let's skip this, maybe saving time. Another characterization for Gorensteinness, we know that a local ring R and M is Gorenstein if and only if R is Cohen-Macaulay and it possesses an irreducible parameter ideal. Parameter ideal means an ideal that is generated by a system of parameters. So by seeing this characterization of Gorenstein local rings, one may ask, is it true that a ring is a relative Gorenstein if and only if it is a relative Cohen-Macaulay and it has an irreducible ideal that is generated by an A relative system of parameters? So this is a natural question, but the answer is again no, as we can see by this example. Here we have a d-dimensional Cohen-Macaulay local ring, and we take a local ring, a d-dimensional local ring, which is Cohen-Macaulay but is not Gorenstein. Let x1 up to xd in M be a system of parameters of R. Since R is Cohen-Macaulay, this system of parameters has to be a regular sequence. Set A be the ideal generated by these D elements. Then R is a relative Gorenstein. It can be seen easily. But this cannot be reducible, because if these or any A relative ideal generated by an A system of parameter cannot be reducible, because it's easy by because of we take an spatial ideal. It's easy to see that any A relative system of parameter is also an ordinary system of parameter. So since R is not Gorenstein, there shouldn't be any reducible ideal that generated by an S a relative system of parameters for R. So next, in this section, we will be focusing on Gorenstein, relative regular modules. Let's skip this example. We have here a nice theorem. If R is a relative regular, then we have this equality, this nice equality. This is the analog of the fact that for a local regular ring, dimension of the ring is the same as the projective dimension of residual field. So this is the analog of that fact. If we try to have this for regular modules, then we should impose an extra assumption on N. So let A be an ideal that is contained in the Jacobson radical of R. Then we have this formula for every A relative regular R module. And here there is a characterization for M relative regular modules. Let A be an ideal which is contained in the Jacobson radical of R, and M be a non-zero finitely generated R module. Then the following are equivalent. M is a relative regular if and only if we have these two equalities. Grade of A and M is a grade of A and R, and it's equal to mu of R. These two conditions are equivalent. Let me skip this and just here we denote the full subcategory of all A relative regular R modules by this notation. I skipped modules and Auslander class and Bus class, but just I recall that there is an equivalence of categories between the Auslander class and Bus class in this way, and we establish this equivalence of categories. We intersect both sides of this equivalence with the subcategory of all A relative Cohen-Macaulay modules and establish these equivalences of categories. And here is a definition, a new definition, like dualizing module. Here we have a relative theory of dualizing module. Let C be homological dimension of A, and R be an A relative Cohen-Macaulay ring. Then A relative dualizing module of R is defined in this way. We have just one non-zero local cohomology, and we call its matrix dual the A relative dualizing module, and denoted by this symbol. So just in 2 minutes, I just mentioned to an explicit question. The theory, there are some works about relative Cohen-Macaulay modules. So even in relative Cohen-Macaulay modules, there are a lot of questions yet. But for other type of relative modules and rings, there are just 1 or 2 papers. So there are a lot of questions that can be asked, and there are a lot of space for further research. But here I just want to propose an explicit question. The existence of big Cohen-Macaulay algebras is very an important question for many decades, and recently answered by Andre using the technique of perfect spaces. We here have we want to propose the relative analog of Huckster conjecture regarding the existence of the Cohen-Macaulay algebra. So first, we should have the notion of relative Cohen-Macaulay modules. Let A be a proper ideal of R with this assumption. You know, this assumption is needed for having a relative system of parameters. Let M be an R module, not necessarily finitely generated. We say that M is a relative Cohen-Macaulay if there exists an A system of parameter of R, which is an M regular sequence. So here is our question. Let A be a proper ideal of R such that this condition is satisfied. Does R admit an irrelative Cohen-Macaulay module? So this is the analog of Huckster conjecture in relative situation. So there are the references for my presentation, and here I end my talk. Thank you for your attention and for being patient.
Thank you. Thank you for a nice talk. Is there any question from the audience?